In this next set of videos, I'd like to tell you about a problem called anomaly detection. This is a reasonably commonly used type of machine learning, and one of its interesting aspects is that it's mainly thought of as an unsupervised learning problem, but there are some aspects of it that are also very similar to sort of a supervised learning problem. So what is anomaly detection? To explain it, let me use the motivating example of imagine that you're a manufacturer of aircraft engines, and let's say that as your aircraft engines roll off the assembly line, you're doing QA, quality assurance testing, and as that part of that testing, you measure features of your aircraft engine, like maybe you measure the heat generated, things like the vibrations, and so on. I actually have some friends that worked on this problem a long time ago, and these were actually the sorts of features that they were collecting off actual aircraft engines. And so you now have a data set of X1 through XM if you have manufactured M aircraft engines. And if you plot your data, maybe it looks like this. So each point here, each cross here is one of your unlabeled examples. So the anomaly detection problem is the following. Let's say that on the next day you have a new aircraft engine that rolls off the assembly line, and your new aircraft engine has some set of features X tests. What the anomaly detection problem is, we want to know if this aircraft engine is anomalous in any way. In other words, we want to know if maybe this engine should undergo further testing, because or if it looks like an okay engine, and so it's okay to just ship it to a customer without further testing. So if your new aircraft engine looks like a point over there, well, that looks a lot like the aircraft engines we've seen before, and so maybe we'll say that it looks okay. Whereas if your new aircraft engine, if X tests, were a point that were out here, so if X1 and X2 of the features of this new example, X tests were all the way out there, then we would call that an anomaly, and maybe send that aircraft engine for further testing before we ship it to a customer, since it looks very different than the rest of the aircraft engines we've seen before. More formally, in the anomaly detection problem, we're given some data sets, X1 through XM of examples, and we usually assume that these M examples are normal or non-anomalous examples, and we want an algorithm to tell us if some new example X test is anomalous. The approach that we're going to take is that given this training set, given the unlabeled training set, we're going to build a model for P of X. In other words, we're going to build a model for the probability of X, where X are these features of, say, aircraft engines. And so, having built a model of the probability of X, we're then going to say that if for the new aircraft engine, if P of X test is less than some epsilon, then we flag this as an anomaly. So we see a new engine that has very low probability under our model P of X that we estimate from the data. Then we flag it as an anomaly. Whereas if P of X test is, say, greater than or equal to some small threshold, then we say that okay, it looks okay. And so given a training set like that plotted here, if you build a model, hopefully we'll find that aircraft engines, hopefully the model P of X will say that points that lie somewhere in the middle, that's pretty high probability, whereas points that are a little bit further out have lower probability, points that are even further out have somewhat lower probability, and a point that's way out here, a point that's way out there would be an anomaly. Whereas for a point that's way in there, right in the middle, this would be okay, because P of X right in the middle of that would be very high, because we've seen a lot of points in that region. Here are some examples of applications of anomaly detection. Perhaps the most common application of anomaly detection is actually fraud detection. If you have many users, and if each of your users take different activities, maybe on your website or in a physical plant or something, you can compute features, xi, of the different users' activities, and what you can do is build a model to say, what is the probability of different users behaving different ways? So what is the probability of a particular vector of features of a user's behavior? So, examples of features of a user's activity may be on the website, it'd be things like maybe X1 is how often does this user log in? X2 maybe the number of web pages visited, or the number of transactions. Maybe X3 is the number of posts of the users on the forum. A feature X4 could be what is the typing speed of the user, and some websites can actually track that. So what's the typing speed of this user in characters per second? And so you can model P of X based on this sort of data. And finally, having modeled P of X, you can try to identify users that are behaving very strangely on your website by checking which ones have probability of X less than epsilon, and maybe send the profiles of those users for further review, or demand additional identification from those users or some such to guard against strange behavior or fraudulent behavior on your website. This sort of technique will tend to flag users that are behaving unusually, not just users that may be behaving fraudulently. So not just accounts that may have been stolen, or users that are trying to do funny things, or just find unusual users. But this is actually the technique that is used by many online websites that sell things to try to identify users behaving strangely, and that might be indicative of either fraudulent behavior or of accounts that have been stolen. Another example of anomaly detection is manufacturing. So already talked about the aircraft engine thing, where we can find unusual, say, aircraft engines and send those for further review. A third application would be monitoring computers in a data center. And I actually have some friends that work on this too. So if you have a lot of machines in a computer cluster or in a data center, you can do things like compute features of each machine. So maybe some features capturing how much memory used, number of disk accesses, CPU load, as well as more complex features like what is the CPU load on this machine divided by the amount of network traffic on this machine. Then, given a data set of how your computers in your data center usually behave, you can model the probability of X. So you can model the probability of these machines having different amounts of memory use, or probably of these machines having different numbers of disk accesses or different CPU loads and so on. And if you ever have a machine whose probability of X, P of X, is very small, then you know that machine is behaving unusually, and maybe that machine is about to go down, and you can flag that for review by a system administrator. And this is actually being used today by various data centers to watch out for unusual things happening on their machines. So that's anomaly detection. In the next video, I'll talk a bit about the Gaussian distribution and review properties of the Gaussian probability distribution. And in videos after that, we'll apply it to develop an anomaly detection algorithm. In this video, I'd like to talk about the Gaussian distribution, which is also called the normal distribution. In case you're already intimately familiar with the Gaussian distribution, it's probably okay to skip this video. But if you're not sure, or if it's been a while since you've worked with the Gaussian distribution or the normal distribution, then please do watch this video all the way to the end. And in the video after this, we'll start applying the Gaussian distribution to developing an anomaly detection algorithm. Let's say X is a real-valued random variable, so X is a real number. If the probability distribution of X is Gaussian with mean mu and variance sigma squared, then we'll write this as X, the random variable, tilde, that's this little tilde, read this is distributed as and then to denote the Gaussian distribution, we're sometimes going to write script n parentheses mu comma sigma squared. So this script n stands for normal, since Gaussian and normal distribution, they mean the same thing, so synonyms. And a Gaussian distribution is parameterized by two parameters, by a mean parameter, which we denote mu, and a variance parameter, which we denote via sigma squared. If we plot the Gaussian distribution, or Gaussian probability density, it'll look like the bell-shaped curve, which you may have seen before. And so this bell-shaped curve is parameterized by those two parameters, mu and sigma. And the location, or the center of this bell-shaped curve, is the mean mu, and the width of this bell-shaped curve, so roughly that, is the this parameter sigma. Is also called one standard deviation. And so this specifies the probability of X taking on different values. So X taking on values, in the middle here is pretty high since the Gaussian density here is pretty high, whereas x taking on values further and further away will be diminishing in probability. Finally, just for completeness, let me write out the formula for the Gaussian distribution. So the probability of x, and I'll sometimes write this instead of p of x, I'm going to write this as p of x semicolon mu comma sigma squared. And so this denotes that the probability of x is parameterized by the two parameters mu and sigma squared. And the formula for the Gaussian density is this 1 over root 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. So there's no need to memorize this formula. This is just the formula for the bell-shaped curve over here on the left. There's no need to memorize it, and if you ever need to use this, you can always look this up. And so that figure on the left, that is what you get if you take a fixed value of mu and take a fixed value of sigma, and you plot p of x. So this curve here, this is really p of x plotted as a function of x, for a fixed value of mu and of sigma squared. And by the way, sometimes it's easier to think in terms of sigma squared, that's called the variance, and sometimes it's easier to think in terms of sigma. So sigma is called the standard deviation, and it sort of specifies the width of this Gaussian probability density, whereas the square of sigma, so sigma squared, is called the variance. Let's look at some examples of what the Gaussian distribution looks like. If mu equals 0, sigma equals 1, then we have a Gaussian distribution that's centered around 0, because that's mu, and the width of this Gaussian, so that's one standard deviation, is sigma over there. Let's look at some examples of Gaussians. If mu is equal to 0 and sigma equals 1, then that corresponds to a Gaussian distribution that is centered at 0, since mu is 0, and the width of this Gaussian is governed or is controlled by sigma, by that variance parameter sigma. Here's another example. Let's say mu is equal to 0 and sigma is equal to 1/2. So the standard deviation is 1/2, and the variance sigma squared would therefore be the square of 0.5, would be 0.25. And in that case, the Gaussian distribution, the Gaussian probability density, looks like this. Is also centered at 0, but now the width of this is much smaller, because with smaller variance, the width of this Gaussian density is roughly half as wide. But because this is a probability distribution, the area under the curve, that is the shaded area there, that area must integrate to 1. This is a property of probability distributions. And so, this is a much taller Gaussian density because it's half as wide with half the standard deviation, but it's twice as tall. Another example, if sigma is equal to 2, then you get a much fatter, a much wider Gaussian density. And so here, the sigma parameter controls that this Gaussian density has a wider width. And once again, the area under the curve, that is this shaded area, it always integrates to 1. That's a property of probability distributions. And because it's wider, it's also half as tall in order to still integrate to the same thing. And finally, one last example would be if we now change the mu parameter as well, then instead of being centered at 0, we now have a Gaussian distribution that's centered at 3, because this shifts over the entire Gaussian distribution. Next, let's talk about the parameter estimation problem. So what's the parameter estimation problem? Let's say we have a data set of m examples, so x1 through xm, and let's say each of these examples is a row number. Here in the figure, I've plotted an example of a data set. So the horizontal axis is the x-axis, and I have a range of examples of x, and I've just plotted them on this figure here. And the parameter estimation problem is, let's say I suspect that these examples came from a Gaussian distribution. So let's say I suspect that each of my examples, xi, was distributed. That's what this tilde thing means. Let's say I suspect that each of these examples was distributed according to a normal distribution or a Gaussian distribution with some parameter mu and some parameter sigma squared. But I don't know what the values of these parameters are. The problem with parameter estimation is, given my data set, I want to try to figure out, or I want to estimate what are the values of mu and sigma squared. So if you're given a data set like this, it looks like maybe if I estimate what Gaussian distribution the data came from, maybe that might be roughly the Gaussian distribution it came from, with mu being the center of the distribution and sigma, the standard deviation, controlling the width of this Gaussian distribution. Right? It seems like a reasonable fit to the data because it looks like the data has a very high probability of being in the central region, low probability of being further out, even low probability of being further out, and so on. So maybe this is a reasonable estimate of mu and of sigma squared. That is, if it corresponds to a Gaussian distribution that looks like this. So what I'm going to do is just write out the formulas, the standard formulas for estimating the parameters mu and sigma squared. Our estimate, or the way we're going to estimate mu, is going to be just the average of my example. So mu is the mean parameter. Just take my training set, take my m examples and average them, and that gives me the center of this distribution. How about sigma squared? Well, the variance, I'll just write out the standard formula again. I'm going to estimate as sum over 1 through m of xi minus mu squared. And so this mu here is actually the mu that I compute over here using this formula. And what the variance is, or one interpretation of the variance, is that if you look at this term, that's the squared difference between the value I got in my example minus the mean, minus the center, minus the mean of the distribution. And so the variance I'm going to estimate as just the average of the squared differences between my examples minus the mean. And as a side comment, only for those of you that are experts in statistics, if you're an expert in statistics and if you've heard of maximum likelihood estimation, then these parameters, these estimates are actually the maximum likelihood estimates of the parameters mu and sigma squared. But if you haven't heard of that before, don't worry about it. All you need to know is that these are the two standard formulas for how you estimate, for how you try to figure out what are mu and sigma squared given the data set. Finally, one last side comment. Again, only for those of you that have maybe taken a statistics class before, but if you've taken a statistics class before, some of you may have seen the formula here where this is m minus 1 instead of m. So this first term becomes 1 over m minus 1 instead of 1 over m. In machine learning, people tend to use this 1 over m formula, but in practice, whether this is 1 over m or 1 over m minus 1, it makes essentially no difference, assuming m is reasonably large, you have like a reasonably large training set size. So just in case you've seen this other version before, in either version works just about equally well, but in machine learning, most people tend to use 1 over m in this formula. And the two versions have slightly different theoretical properties, slightly different mathematical properties, but in practice it really makes very little difference, if any. So hopefully you now have a good sense of what the Gaussian distribution looks like, as well as how to estimate the parameters mu and sigma squared of a Gaussian distribution if you're given a training set, that is, if you're given a set of data that you suspect comes from a Gaussian distribution with unknown parameters mu and sigma squared. In the next video, we'll start to take this and apply it to develop an anomaly detection algorithm. In the last video, we talked about the Gaussian distribution. In this video, let's apply that to develop an anomaly detection algorithm. Let's say that we have an unlabeled training set of m examples, and each of these examples is going to be a feature in Rn. So your training set could be m feature vectors from the last m aircraft engines that you manufactured, or it could be features from m users or something else. The way we're going to address anomaly detection is we're going to model p of x from this data set. So we'll try to figure out what are high probability features and what are low probability types of features. So x is a vector, and what we're going to do is model p of x as probability of x1, that is of the first component of x, times the probability of x2, so probability of the second feature, times the probability of the third feature, and so on, up to the probability of the final feature xn. I'm leaving space here because I'll fill in something in a minute. So how do we model each of these terms, p of x1, p of x2, and so on? What we're going to do is assume that the feature x1 is distributed according to a Gaussian distribution with some mean, which I'm going to write as mu1, and some variance, which I'm going to write as sigma squared 1. And so P of x1 is going to be a Gaussian probability distribution with mean mu1 and variance sigma squared 1. And similarly, I'm going to assume that x2 is distributed Gaussian. That's what this little tilde stands for. That means distributed. This distributed Gaussian with mean mu2 and sigma squared 2. So it's distributed according to a different Gaussian, which has a different set of parameters, mu2 sigma squared 2. And similarly, x3 is yet another Gaussian, and so this can have a different mean and a different standard deviation than the other features, and so on up to xn. And so that's my model. Just as a side comment for those of you that are experts in statistics, it turns out that this equation that I just wrote out actually corresponds to an independence assumption on the values of the features x1 through xn. But in practice, it turns out that the algorithm I'm going to describe, it works just fine whether or not these features are anywhere close to independence. And even if independence assumption doesn't hold true, this algorithm works just fine. But in case you don't know those terms I just used of independence assumptions and so on, don't worry about it. You'll be able to understand and implement this algorithm just fine. And that comment was really meant only for the experts in statistics. And finally, in order to wrap this up, let me take this expression and write it a little bit more compactly. So I'm going to write this is a product from j equals 1 through n of p of xj parameterized by mu j comma sigma squared j. So this funny symbol here, this is actually a capital Greek alphabet pi. That funny symbol there corresponds to taking the product of a set of values. And so, you're familiar with the summation notation. So if I write sum from I equals 1 through n, of I, this means 1 plus 2 plus 3 plus dot 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 up to n. Whereas this funny symbol here, this product symbol, right, product from I equals 1 through n of I, then this means that it's just like summation, except that we're now multiplying. So this becomes 1 times 2 times 3 times dot 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 up to n. And so using this product notation, this product from j equals 1 through n of this expression, that's just a more compact, or like a shorter way of writing out this huge product of all of these terms up there. Since we're taking these p of xj given mu j comma sigma squared j terms and we're multiplying them together. And by the way, the problem of estimating this distribution p of x is sometimes called the problem of density estimation, so hence the title of the slide. So, putting everything together, here's our anomaly detection algorithm. The first step is to choose features or come up with features xi that we think might be indicative of anomalous examples. So what I mean by that is try to come up with features so that when there's an unusual user in your system that may be doing fraudulent things, or when, for the aircraft engine example, when there's something funny, something strange about one of the aircraft engines, choose features xi that you think might take on unusually large values or unusually small values for what an anomalous example might look like. But more generally, just try to choose features that describe what you think that describe general properties of the things that you're collecting data on. Next, given a training set of m unlabeled examples, so x1 through xm, we then fit the parameters mu1 through mu n and sigma squared 1 through sigma squared n. And so these were the formulas similar to the formulas we had in the previous video that we're going to use to estimate each of these parameters. And just to give some interpretation, mu j, that's my average value of the j feature, right? So mu j goes in this term p of xj, which is parameterized by mu j and sigma squared j. And so this says, for the mu j, just take the mean over my training set of the values of the j feature. And I just mentioned that you do this, you compute these formulas for j equals 1 through n. So you use these formulas to estimate mu1, to estimate mu2, and so on up to mu n, and similarly for sigma squared. And it's also possible to come up with vectorized versions of these. So if you think of mu as a vector, so if mu is a vector, there's mu1, mu2, down to mu n, then a vectorized version of that set of parameters can be written like so. Sum from I equals 1 through m xi. And so this formula that I just wrote out estimates, where these xi are the feature vectors, this estimates mu for all the values of n simultaneously. And it's also possible to come up with a vectorized formula for estimating sigma squared j. Finally, when you're given a new example, so when you have a new aircraft engine and you want to know, is this aircraft engine anomalous? What we need to do is then compute p of x. What's the probability of this new example? So p of x is equal to this product, and what you implement, what you compute is this formula, and where over here, this thing here is just the formula for the Gaussian probability, and so you compute this thing, and finally, if this probability is very small, you then flag this thing as an anomaly. Here's an example of an application of this method. Let's say we have this data set that I've plotted on the upper left of this slide. If you look at this, well, let's look at the features of x1. If you look at this data set, it looks like on average, the features x1 has a mean of about 5, and the standard deviation, if you look at just the x1 values of this data set, it has a standard deviation of maybe 2, so that's sigma 1. And looks like the x2, the values of the features as measured on the vertical axis, it looks like that has an average value of about 3 and a standard deviation of about 1. So if you take this data set and if you estimate, mu1, mu2, sigma 1, sigma 2, this is what you get. And again, I'm writing sigma here, thinking of standard deviations, but the formula on the previous slide actually gave estimates for the squares of these things, right? So sigma squared 1 and sigma squared 2. So just be careful whether you're using sigma 1, sigma 2, or sigma squared 1 or sigma squared 2. So sigma squared 1, of course, would be equal to 4, for example, as a square of 2. And in pictures, what p of x1 parameterized by mu1 and sigma squared 1, and p of x2 parameterized by mu2 and sigma squared 2, that would look like these two distributions over here. And it turns out that if you were to plot p of x, right, which is the product of these two things, you can actually get a surface plot that looks like this. So this is a plot of p of x where the height above this, where the height of this surface at a particular point, so given a particular x1, x2 values of if x1 equals 2, x2 equals 2, that's this point, and the height of this 3D surface here, that's p of x. So p of x, that is the height of this plot. This is literally just p of x1 parameterized by mu1 sigma squared 1 times p of x2 parameterized by mu2 sigma squared 2. Now, so this is how we fit the parameters to this data. Let's say we have a couple new examples. Maybe I have a new example there. Is this an anomaly or not? Or maybe I have a different example. Maybe I have a second example over there. So is that an anomaly or not? The way we do that is we would set some value for epsilon. Let's say I've chosen epsilon equals 0.02. I'll say later how we choose epsilon. But let's take this first example. Let me call this example x1 test. And let me call the second example, x2 test. What we do is we then compute p of x1 test. So we use this formula to compute it, and this looks like a pretty large value. In particular, this is greater than or greater than or equal to epsilon, and so there's a pretty high probability, at least bigger than epsilon, so we'll say that x1 test is not an anomaly. Whereas if you compute p of x2 test, well, that gives a much smaller value, so this is less than epsilon, and so we'll say that that is indeed an anomaly because it's much smaller than that epsilon that we chose. And in fact, I didn't prove it here. What this is really saying is that if you look at this 3D surface plot, it's saying that all the values of x1 and x2 that have a high height above the surface corresponds to a non-anomalous or sort of an okay or normal example, whereas all the points far out here, all the points out here, all those points have very low probability, and so we're going to flag those points as anomalous, and so it's going to define some region that maybe looks like this, so that everything outside this it flags as anomalous, whereas the things inside this ellipse I just drew, if it considers okay or non-anomalous, not anomalous examples. And so this example, x2 test, lies outside that region, so it has very small probability, and so we consider it an anomalous example. In this video, we talked about how to estimate P of x, the probability of x, for the purpose of developing an anomaly detection algorithm. And in this video, we also stepped through an entire process of getting a data set, fitting the parameters, doing parameter estimation to get mu and sigma parameters, and then taking new examples and deciding if the new examples are anomalous or not. In the next few videos, we'll delve deeper into this algorithm and talk a bit more about how to actually get this to work well. In the last video, we developed an anomaly detection algorithm. In this video, I'd like to talk about the process of how to go about developing a specific application of anomaly detection to a problem. And in particular, this will focus on the problem of how to evaluate an anomaly detection algorithm. In previous videos, we'd already talked about the importance of row number evaluation, and this captures the idea that when you're trying to develop a learning algorithm for a specific application, you need to often make a lot of choices, like choosing what features to use and so on. And making decisions about all of these choices is often much easier if you have a way to evaluate your learning algorithm that just gives you back a number. So if you're trying to decide, I have an idea for one extra feature, do I include this feature or not? If you can run the algorithm with the feature and run the algorithm without the feature and just get back a number that tells you, did it improve or worsen performance to add this feature, then it gives you a much better way, a much simpler way with which to decide whether or not to include that feature. So in order to be able to develop an anomaly detection system quickly, it's really helpful to have a way of evaluating an anomaly detection system. In order to do this, in order to evaluate an anomaly detection system, we're actually going to assume that we have some labeled data. So far we'll be treating anomaly detection as an unsupervised learning problem using unlabeled data. But if you have some labeled data that specifies what are some anomalous examples and what are some non-anomalous examples, then this is how we actually think of as the standard way of evaluating an anomaly detection algorithm. So taking the aircraft engine example again, let's say that you have some labeled data of a lot of just a few anomalous examples of some aircraft engines that were manufactured in the past that turned out to be anomalous, it turned out to be flawed or strange in some way. And let's say we also have some non-anomalous examples of some perfectly okay examples. So I'm going to use y equals 0 to denote the normal or the non-anomalous examples, and y equals 1 to denote the anomalous examples. The process of developing and evaluating an anomaly detection algorithm is then as follows. We're going to think of as the training set. We'll talk about the cross-validation and test sets later, but the training set, we usually think of this as still the unlabeled training set. And so this is our large collection of normal, non-anomalous or not anomalous examples. And usually we think of this as being non-anomalous, but it's actually okay even if a few anomalies slip into your unlabeled training set. And next we're going to define a cross-validation set and a test set with which to evaluate a particular anomaly detection algorithm. So specifically for both the cross-validation and test sets, we're going to assume that we can include a few examples in the cross-validation set and the test set that contain examples that are known to be anomalous. So the test set, say, we'll have a few examples with y equals 1 that correspond to anomalous aircraft engines. So here's a specific example. Let's say that altogether, this is the data that we have. We have manufactured 10,000 examples of engines that, as far as we know, were perfectly normal, perfectly good aircraft engines. And again, it turns out to be okay, even if a few flawed engine slips into this set of 10,000 is actually okay, but we kind of assume that the vast majority of these 10,000 examples are good or normal, non-anomalous engines. And let's say that historically in however long we've been running our manufacturing plant, let's say that we end up getting 20 flawed or 20 anomalous engines as well. And for a pretty typical application of anomaly detection, the number of known anomalous examples, that is with y equals 1, we may have anywhere from 20 to 50 would be a pretty typical range of examples, number of examples that we have with y equals 1. And usually we'll have a much larger number of good examples. So given this data set, a fairly typical way to split it into the training set, cross-validation set, and test set would be as follows. Let's take out 10,000 good aircraft engines and put 6,000 of that into the unlabeled training set. So this is, I'm calling this an unlabeled training set, but all of these examples are really ones that correspond to y equals 0 as far as we know. And so we would use this to fit P of x, right? So we would use these 6,000 engines to fit P of x, which was that P of x1 parameterized by mu1 sigma squared 1 up to P of xn parameterized by mu n sigma squared n. And so it would be these 6,000 examples that we would use to estimate the parameters mu1 sigma squared 1 up to mu n sigma squared n. So that's our training set of all good or the vast majority of good examples. Next, we would take our good aircraft engines and put some number of them in the cross-validation set, put some number of them in the test set. So that's 6,000 plus 2,000 plus 2,000. That's how we split up our 10,000 good aircraft engines. And then we also have 20 flawed aircraft engines, and we'll take that and maybe split it up. Put 10 of them in the cross-validation set and put 10 of them in the test set. And in the next slide, we'll talk about how to actually use this to evaluate the anomaly detection algorithm. So what I've just described here is probably the recommended or pretty good way of splitting the labeled and unlabeled example, the good and the flawed aircraft engines, where we use like a 60-20% split for the good engines, and we take the flawed engines and we put them just in the cross-validation set and just in the test set. And we'll see in the next slide why that's the case. Just as an aside, if you look at how people apply anomaly detection algorithms, sometimes you see other people split the data differently as well. So another alternative, this is really not a recommended alternative, but some people will take of your 10,000 good engines, maybe put 6,000 of them in the training set, and then put the same 4,000 in the cross-validation set in the test set. And so, we like to think of the cross-validation set and the test set as being completely different data sets than each other. But in anomaly detection, for sometimes you see people sort of use the same set of good engines in the cross-validation set and the test sets, and sometimes you see people use exactly the same set of anomalous engines in the cross-validation set and the test set. And so all of these are considered less good practices and definitely less recommended. Certainly, right, using the same data in the cross-validation set and the test set, that's sort of not considered good machine learning practice. But sometimes you see people do this too. So given the training, cross-validation, and test sets, here's how you evaluate, or here's how you develop and evaluate an algorithm. First, we take the training set and we fit the model P of x, so we fit all those Gaussians to my m unlabeled examples of aircraft engines, and these are, I'm calling them unlabeled examples, but these are really examples that we're assuming are good or the normal aircraft engines. Then imagine that your anomaly detection algorithm is actually making predictions. So on the cross-validation of the test set, given a, say, test example x, think of the algorithm as predicting that y is equal to 1, P of x is less than epsilon, is predicting 0 if P of x is greater than or equal to epsilon. So it's trying to predict, given x, is trying to predict what is the label. Is it y equals 1 corresponding to an anomaly, or is it y equals 0 corresponding to a normal example? So given the training, cross-validation, and test sets, how do you develop an algorithm, and more specifically, how do you evaluate an anomaly detection algorithm? Well, to do so, the first step is to take the unlabeled training set and to fit the model P of x to the training data. So you take this, I'm calling it unlabeled training set, but really these are examples that we're assuming the vast majority of which are normal aircraft engines, not anomalies, and we're going to fit the model P of x. We're going to fit all those parameters for all the Gaussians on this data. Next, on the cross-validation of the test set, we're going to think of the anomaly detection algorithm as trying to predict the value of y. So in each of my, say, test examples, we have these xi tests, yi tests, where y is going to be equal to 1 or 0, depending on whether this was an anomalous example. So given input x in my test set, my anomaly detection algorithm, think of that as predicting that y is 1, if p of x is less than epsilon, so predicting that is an anomaly, the probability is very low. And we think of the algorithm as predicting that y is equal to 0 if p of x is greater than or equal to epsilon, so predicting that is a normal example if the p of x is reasonably large. And so we can now think of the anomaly detection algorithm as making predictions for what are the values of these y labels in the test sets or in the cross-validation set. And this puts us somewhat more similar to the supervised learning setting, right, where we have like a label test set and our algorithm is making predictions on these labels, and so we can evaluate it, by seeing how often it gets these labels right. Of course, these labels will be very skewed because y equals 0, that is normal examples, will usually be much more common than y equals 1, than anomalous examples. But this is much closer to the sorts of evaluation metrics we can use in supervised learning. So what's a good evaluation metric to use? Well, because the data, because the data is very skewed, because y equals 0 is much more common, classification accuracy would not be a good evaluation metric. So we talked about this in the earlier video. If you have a very skewed data set, then predicting y equals 0 all the time will have very high classification accuracy. Instead, we should use evaluation metrics like computing the fraction of true positives, false negatives, true negatives, compute things like that, or compute the precision and recall of this algorithm, and, or do things like compute the F1 score, right, which is a single row number way of summarizing the precision and the recall numbers. And so these would be ways to evaluate an anomaly detection algorithm on your cross-validation set or on your test set. Finally, earlier in the anomaly detection algorithm, we also had this parameter epsilon, right? So epsilon was this threshold that we would use to decide when to flag something as an anomaly. And so if you have a cross-validation set, one way to choose this parameter epsilon would be to try many different values of epsilon, and then pick the value of epsilon that, let's say, maximizes F1 score, or that otherwise does well on your cross-validation set. And more generally, the way to use the training, testing, and cross-validation sets is that when we're trying to make decisions like what features to include, or trying to tune the parameter epsilon, we would then continually evaluate the algorithm on the cross-validation set. So we make all those decisions like what features to use, how to set epsilon, use that, evaluate the algorithm on the cross-validation set, and then when we've picked a set of features, when we've found the value of epsilon that we're happy with, we can then take the final model and evaluate it, do the final evaluation of the algorithm on the test set. So in this video, we talked about the process of how to evaluate an anomaly detection algorithm. And again, being able to evaluate an algorithm with a single row number evaluation, with a number like an F1 score, that often allows you to make much more efficient use of your time when you're trying to develop an anomaly detection system. And we're trying to make these sorts of decisions like how to choose epsilon, what features to include, and so on. In this video, we started to use a bit of label data in order to evaluate the anomaly detection algorithm. And this takes us a little bit closer to a supervised learning setting. In the next video, I'm going to say a bit more about that, and in particular, we'll talk about when should you be using an anomaly detection algorithm, and when should we be thinking about using supervised learning instead, and what are the differences between these two formalisms. In the last video, we talked about the process of evaluating an anomaly detection algorithm, and there we started to use some label data with examples that we knew were either anomalous or not anomalous, with y equals 1 or y equals 0. And so the question then arises of, if we have this label data, if we have some examples that are known to be anomalies and some that are known not to be anomalies, why don't we just use a supervised learning algorithm? So why don't we just use logistic regression or a neural network to try to learn directly from our label data to predict whether y equals 1 or y equals 0. In this video, I'll try to share with you some of the thinking and some guidelines for when you should probably use an anomaly detection algorithm and when it might be more fruitful to consider using a supervised learning algorithm. This slide shows what are the settings under which you should maybe use anomaly detection versus when supervised learning might be more fruitful. If you have a problem with a very small number of positive examples, and remember, examples of y equals 1 are the anomalous examples, then you might consider using an anomaly detection algorithm instead. So having 0 to 20, maybe up to 50 positive examples might be pretty typical. And usually we have such a small positive set of positive examples, we're going to save the positive examples just for the cross-validation set and the test set. And in contrast, in a typical normal anomaly detection setting, we will often have a relatively large number of negative examples of the normal examples of normal aircraft engines, and we can then use this very large number of negative examples with which to fit the model P of X. And so there's this idea that in many anomaly detection applications, you have very few positive examples and lots of negative examples, and when we're doing the process of estimating P of X, of fitting all those Gaussian parameters, we need only negative examples to do that. So if you have a lot of negative data, we can still fit P of X pretty well. In contrast, for supervised learning, more typically we would have a reasonably large number of both positive and negative examples. And so this is one way to look at your problem and decide if you should use an anomaly detection algorithm or a supervised learning algorithm. Here's another way that people often think about anomaly detection algorithms. So for anomaly detection applications, often there are many different types of anomalies. So think about aircraft engines. There are so many different ways for aircraft engines to go wrong, right? There's so many things that could go wrong that could break in an aircraft engine. And so if that's the case, and if you have a pretty small set of positive examples, then it can be hard for an algorithm, difficult for an algorithm, to learn from your small set of positive examples what the anomalies look like. And in particular, future anomalies may look nothing like the ones you've seen so far. So maybe in your set of positive examples, maybe you've seen 5 or 10 or 20 different ways that an aircraft engine could go wrong. But maybe tomorrow you need to detect a totally new set, a totally new type of anomaly, a totally new way for an aircraft engine to be broken that you've just never seen before. And if that's the case, then it might be more promising to just model the negative examples with this sort of a Gaussian model P of X, rather than try too hard to model the positive examples, because tomorrow's anomaly may be nothing like the ones you've seen so far. In contrast, in some other problems, you have enough positive examples for an algorithm to get a sense of what the positive examples are like. And in particular, if you think that future positive examples are likely to be similar to ones in the training set, then in that setting, it might be more reasonable to have a supervised learning algorithm that looks at a lot of positive examples, looks at a lot of negative examples, and uses that to try to distinguish between positives and negatives. So hopefully this gives you a sense of, if you have a specific problem, should you think about using an anomaly detection algorithm or a supervised learning algorithm. And the key difference really is that in anomaly detection, often we have such a small number of positive examples that it's not possible for a learning algorithm to learn that much from the positive examples. And so what we do instead is take a large set of negative examples and have it just learn a lot, learn P of X from just the negative examples of the normal aircraft engine, say, and we reserve the small number of positive examples for evaluating our algorithm to use in either the cross-validation set or the test set. And just as a side comment about this, many different types of anomalies. In some earlier videos, we talked about the email spam examples. In those examples, there are actually many different types of spam email, right? The spam email that's trying to sell you things, spam email trying to steal your passwords, it's called phishing emails, and many different types of spam emails. But for the spam problem, we usually have enough examples of spam email to see, most of these different types of spam email, because we have a large set of examples of spam, and that's why we usually think of spam as a supervised learning setting, even though, there are many different types of spam email. And so if we look at some applications of anomaly detection versus supervised learning, we'll find that in fraud detection, if you have many different types of ways for people to try to commit fraud and a relatively small training set, a small number of fraudulent users on your website, then not use an anomaly detection algorithm. I should say, if you're a very major, online retailer, and if you actually have had a lot of people try to commit fraud on your website, so if you actually have a lot of examples with y=1, then sometimes fraud detection could actually shift over to the supervised learning column. But if you haven't seen that many examples of users doing strange things on your website, then more frequently fraud detection is actually treated as an anomaly detection algorithm rather than with a supervised learning algorithm. Other examples, we talked about manufacturing already. Hopefully you've seen more normal examples and not that many anomalies. But if again, for some manufacturing processes, if you manufacture in very large volumes and if you've seen a lot of bad examples, maybe manufacturing could shift to the supervised learning column as well. But if you haven't seen that many bad examples of your own products, then I do this anomaly detection. Monitoring machines at the data center, again, similar sorts of arguments apply. Whereas email spam classification, weather prediction, and classifying cancers, if you have equal numbers of positive and negative examples, or if you have many examples of your positive and your negative examples, then we would tend to treat all of these as supervised learning problems. So hopefully that gives you a sense of what are the properties of a learning problem that would cause you to treat it as an anomaly detection problem versus a supervised learning problem. And for many of the problems that are faced by various technology companies and so on, we actually are in these settings where we have very few or sometimes zero positive training examples. Maybe just there's so many different types of anomalies, we've never seen them before. And for those sorts of problems, very often the algorithm that is used is an anomaly detection algorithm. By now, you've seen the anomaly detection algorithm, and we've also talked about how to evaluate an anomaly detection algorithm. It turns out that when you're applying anomaly detection, one of the things that has a huge effect on how well it does is what features you use or what features you choose to give the anomaly detection algorithm. So in this video, what I'd like to do is say a few words, give some suggestions and guidelines for how to go about designing or selecting features to give to your anomaly detection algorithm. In our anomaly detection algorithm, one of the things we did was model the features using this sort of Gaussian distribution with xi, mu I, comma, sigma squared I, let's say. And so one of the things I often do will be to plot the data or plot a histogram of the data to make sure that the data actually looks vaguely Gaussian before feeding it to my anomaly detection algorithm. And it will usually work okay even if your data isn't Gaussian, but it's sort of a nice sanity check to run. But by the way, in case the data looks non-Gaussian, the algorithm will often work just fine. But concretely, if I plot the data like this, and if it looks like a histogram like this, and the way to plot a histogram is to use the HIST or the HIST command in Octave. But it looks like this. This looks vaguely Gaussian, so if my features look like this, I'd be pretty happy feeding it to my algorithm. But if I were to plot a histogram of my data, and if it were to look like this, well, this doesn't look at all like a bell-shaped curve, right? This is a very asymmetric distribution. It has a peak way off to one side. If this is what my data looks like, what I'll often do is play with different transformations of the data in order to make it look more Gaussian. And again, the algorithm will usually work okay even if you don't, but if you use these transformations to make your data more Gaussian, it might work a bit better. So given a data set that looks like this, what I might do is say take a log transformation of the data, and if I do that and replot the histogram, what I end up with in this particular example is a histogram that looks like this. And this looks much more Gaussian, right? This looks much more like the classic bell-shaped curve that we can fit with some mean and some variance parameter sigma. So what I mean by taking the log transform is really that if I have some feature x1 and the histogram of x1 looks like this, then I might take my feature x1 and replace it with log of x1, and this is my new x1 that I plotted the histogram of on the right. This looks much more Gaussian. And rather than just a log transform, some other things you could do might be, let's say I have a different feature x2, maybe I replace that with log x plus 1, or more generally with log x, maybe that's x2, plus some constant c, and this constant could be something that I play with to try to make it look as Gaussian as possible. Or for a different feature x3, maybe I'll replace it with x3. I might take the square root. Square root is just x3 to the power of 1/2, right? And this 1/2 is another example of a parameter I can play with. So I might have, x4. Maybe I'll instead replace that with x4 to the power of something else, maybe to the power of 1/3. And all of these, this exponent parameter or the C parameter, all of these are examples of parameters you can play with in order to make your data look a little bit more Gaussian. So let me show you a live demo of how I'd actually go about playing around with my data to make it look more Gaussian. So I have already loaded into Octave here a set of features X. So I have 1,000 examples loaded over there. So let's plot a histogram of my data. I'm going to use the hist_x command. So there's my histogram. By default, I think this uses 10 bins in histogram, but I want to see a more fine-grained histogram. So I'm going to use hist of x, 50. So this plots it in 50 different bins. Okay, that looks better. Now, this doesn't look very Gaussian, does it? So let's start playing around with the data. Let's try hist of x to the 0.5. So we'll take the square root of the data and plot that histogram. And okay, it looks a little bit more Gaussian, but not quite there. So let's play with the 0.5 parameter. Let me set this to 0.2. Looks a little bit more Gaussian. Let's reduce a little bit more. 0.1. Yeah, that looks pretty good. I could actually just use 0.1. Well, let's reduce it to 0.05. And okay, this looks pretty Gaussian. So I could define a new feature, which is x new equals x element-wise exponentiation to the 0.05, and now my new feature x new looks more Gaussian than my previous one, and I might instead use this new feature to feed into my anomaly detection algorithm. And of course, there's more than one way to do this. You could also have hist of log of x. That's another example of a transformation you could use. And that also looks pretty Gaussian. So I could also define x new equals log of x, and that would be another pretty good choice of feature to use. So to summarize, if you plot a histogram with the data and find that it looks pretty non-Gaussian, it's worth playing around a little bit with different transformations like these to see if you can make your data look a little bit more Gaussian before you feed it to your learning algorithm. Although even if you don't, it might work okay, but I usually do take this step. Now, the second thing I want to talk about is how do you come up with features for an anomaly detection algorithm? And the way I often do so is via an error analysis procedure. So what I mean by that is that this is really similar to the error analysis procedure that we had for supervised learning, where we would train a complete algorithm and run the algorithm on a cross-validation set and look at the examples it gets wrong and see if we can come up with extra features to help the algorithm do better on the examples that it got wrong in the cross-validation set. So let's look through let's try to reason through an example of this process. In anomaly detection, we're hoping that P of x will be large for the normal examples and it'll be small for the anomalous examples. And so a pretty common problem would be if P of x is comparable, maybe both are large for both the normal and the anomalous examples. Let's look at a specific example of that. Let's say that this is my unlabeled data. So here I have just one feature x1. And so I'm going to fit a Gaussian to this. And maybe my Gaussian that fit to my data looks like that. And now, let's say I have an anomalous example. Let's say my anomalous example takes on an x value of 2.5. So I'm going to plot my anomalous example there. And it's kind of buried in the middle of a bunch of normal examples. And so this anomalous example that I've drawn in green, it gets a pretty high probability, right? It's the height of the blue curve. And the algorithm fails to flag this as an anomalous example. Now, if this were maybe aircraft engine manufacturing or something, what I would do is I would actually look at my training examples and look at what went wrong with that particular aircraft engine and see if looking at that example can inspire me to come up with a new feature x2 that helps to distinguish between this bad example compared to the rest of my red examples, compared to all of my normal aircraft engines. And if I manage to do so, the hope would be then that if I can create a new feature x2 so that when I replot my data, if I take all my normal examples of my training set, hopefully I find that all my training examples are these red crosses here. And hopefully, if I find that for my anomalous example, the feature x2 takes on a very unusual value. So for my green example here, this anomaly, right, my x1 value is still 2.5, but maybe my x2 value, hopefully it takes on a very large value, like 3.5 over there, or a very small value. But now, if I model my data, I'll find that my anomaly detection algorithm gives high probability, to data in the central region, slightly lower probability to that, slightly lower probability to that. An example, and then an example that's all the way out there, my algorithm will now give very low probability to. And so the process of this is really, look at the mistakes that it's making, look at the anomaly that the algorithm is failing to flag, and see if that inspires you to create some new feature. So find something unusual about that aircraft engine and use that to create a new feature, so that with this new feature, it becomes easier to distinguish the anomalies from good examples. And so that's the process of error analysis and using that to create new features for anomaly detection. Finally, let me share with you my thinking on how I usually go about choosing features for anomaly detection. So usually, the way I think about choosing features is I want to choose features that might take on either very, very large values or very, very small values for examples that I think might turn out to be anomalies. So let's use our example again of monitoring the computers in a data center. And so with lots of machines, maybe thousands or tens of thousands of machines in a data center, and we want to know if one of the machines, one of our computers, is acting up to doing something strange. So here are examples of features we might choose, right? Maybe a memory use, number of disk accesses, CPU load, network traffic. But now let's say that I suspect one of the failure cases, let's say that in my data set, I think that CPU load and network traffic tend to grow linearly with each other. Maybe I'm running a bunch of web servers, and so if one of my servers is serving a lot of users, I have a very high CPU load and I have a very high network traffic. But let's say I have a suspicion that one of the failure cases is if one of my computers has a job that gets stuck in some infinite loop. So if I think one of the failure cases is one of the machines, one of my web server code gets stuck in some infinite loop, and so the CPU load grows, but the network traffic doesn't, because it's just spinning its wheels and doing a lot of CPU work, stuck in some infinite loop. In that case, to detect that type of anomaly, I might create a new feature, x5, which might be CPU load divided by network traffic. And so here, x5 will take on an unusually large value if one of the machines has a very large CPU load but not that much network traffic. And so this will be a feature that will help your anomaly detection capture a certain type of anomaly. And you can also get creative and come up with other features as well. Like maybe I have a feature x6 that's CPU load squared divided by network traffic. And this would be another variant of a feature like x5 to try to capture anomalies where one of your machines has a very high CPU load but maybe doesn't have a commensurately large network traffic. And by creating features like these, you can start to capture anomalies that correspond to particular unusual combinations of values of the features. So in this video, we talked about how to take a feature and maybe transform it a little bit so that it becomes a bit more Gaussian before feeding into an anomaly detection algorithm, and also the error analysis in this process of creating features to try to capture different types of anomalies. And with these sorts of guidelines, hopefully that will help you to choose good features to give to your anomaly detection algorithm to help it capture all sorts of anomalies. In this and the next video, I'd like to tell you about one possible extension to the anomaly detection algorithm that we've developed so far. This extension uses something called the multivariate Gaussian distribution. It has some advantages and some disadvantages, and it can sometimes catch some anomalies that the earlier algorithm didn't. To motivate this, let's start with an example. Let's say that our unlabeled data looks like what I plotted here, and I'm going to use the example of monitoring machines in the data center, monitoring computers in the data center. So my two features are x1, which is the CPU load, and x2, which is maybe the memory use. So if I take my two features, x1 and x2, and if I model them as Gaussians, then here's a plot of my x1 features, here's a plot of my x2 features, and so if I fit a Gaussian to that, maybe I'll get a Gaussian like this. So here's p of x1, which depends on my parameters mu1 and sigma squared 1. And here's my memory use. Maybe I get a Gaussian that looks like this. And this is my p of x2, which depends on mu2 and sigma squared 2. And so this is how the anomaly detection algorithm models x1 and x2. Now let's say that in the test set I have an example that looks like this, right? The location of that green cross. So the value of x1 is about 0.4 and the value of x2 is about 1.5. Now if you look at the data, it looks like most of the data lies in this region, and so that green cross is pretty far away from any of the data I've seen. It looks like that should be raised as an anomaly, right? So in my data, in the data of my good examples, it looks like the CPU load and the memory use, they sort of grow linearly with each other. So if I have a machine using lots of CPU, memory use will also be very high. Whereas this example, this green example, it looks like here the CPU load is very low, but the memory use is very high, and I just have not seen that before in my training set. It looks like that should be an anomaly. But let's see what the anomaly detection algorithm will do. Well, for the CPU load, it puts it at around there, 0.5. And this reasonably high probability is not that far from other examples we've seen maybe. Whereas for the memory use, I guess applying it at 0.5. Whereas for the memory use, it's about 1.5, which is there. Again, is out towards the tail of the Gaussian, but the value here is not that different from many other examples we've seen. And so P of x1 will be pretty high, reasonably high. P of x2 will be reasonably high. I mean, if you look at this plot, right, this point here, it doesn't look that bad. And if you look at this plot, across here, it doesn't look that bad. I mean, I have had examples with even greater memory use or with even less CPU use, and so this example doesn't look that anomalous. And so anomaly detection algorithm will fail to flag this point as an anomaly. And it turns out that what our anomaly detection algorithm is doing is it's not realizing that this blue ellipse shows the high probability region. Instead, what it thinks is that examples here are high probability, and examples the next circle out are somewhat lower probability, and examples here are even lower probability. And somehow, things that are green cross there is pretty high probability. And in particular, it tends to think that everything in this region, everything on the line that I'm circling over has about equal probability, and it doesn't realize that something out here actually has much lower probability than something over there. So in order to fix this, we're going to develop a modified version of the anomaly detection algorithm using something called the multivariate Gaussian distribution, also called the multivariate normal distribution. So here's what we're going to do. We have features x which are in Rn, and instead of modeling p of x1, p of x2 separately, we're going to model p of x all in one go. So model p of x all at the same time. So the parameters of the multivariate Gaussian distribution are mu, which is a vector, and sigma, which is an n by n matrix called a covariance matrix. And this is similar to the covariance matrix that we saw when we were working with the PCA, with the principal components analysis algorithm. For the sake of completeness, let me just write out the formula for the multivariate Gaussian distribution. So we say that probability of x, and this is parameterized by my parameters mu and sigma, but the probability of x is equal to, once again, there's absolutely no need to memorize this formula. You can look it up whenever you need to use it, but this is what the probability of x looks like. Transpose sigma inverse x minus mu. And this thing here, the absolute value of sigma, this thing here, when I write this symbol, this is called the determinant of sigma. And this is a mathematical function of a matrix, and you really don't need to know what the determinant of a matrix is, but really all you need to know is that you can compute it in octave by using the octave command det of sigma. Okay, and again, just be clear, right? In this expression, these sigmas here, these are this n by n matrix. This is not a summation. That sigma there is an n by n matrix. So that's the formula for P of x. But more interestingly, or more importantly, is what does P of x actually look like? Let's look at some examples of multivariate or Gaussian distributions. So let's take a two-dimensional example. So if I have n equals 2, I have two features, x1 and x2. Let's say I set mu to be equal to 0 and sigma to be equal to this matrix here, with 1s on the diagonals and 0s on the off diagonals. This matrix is sometimes also called the identity matrix. In that case, P of x will look like this. And what I'm showing this figure is, for a specific value of x1 and for a specific value of x2, the height of this surface gives the value of P of x. And so with this setting of the parameters, P of x is highest when x1 and x2 equals 0. So that's the peak of this Gaussian distribution. And the probability falls off with this sort of two-dimensional Gaussian, or this bell-shaped, two-dimensional bell-shaped surface. Down below is the same thing but plotted using a contour plot instead, or plotted using the different colors. And so there's a heavy intense red in the middle corresponds to the highest values, and then the values decrease, with the yellow being slightly lower values, the cyan being lower values, and this deep blue being the lowest value. So this is really the same figure but plotted viewed from the top instead, using colors instead. And so with this distribution, you see that it places most of the probability near 0, 0, and then as you go away from 0, 0, the probability of x1 and x2 goes down. Now let's try varying some of the parameters and see what happens. So let's take sigma and change it. So let's say sigma shrinks a little bit. Sigma is a covariance matrix, and so it measures the variance of the variability of the features x1 and x2. So if you shrink sigma, then what you get is that the width of this bump diminishes, and the height also increases a bit, because the area under the surface is equal to 1. So the integral of the volume under the surface is equal to 1, because probability distribution must integrate to 1. But so if you shrink the variance, it's kind of like shrinking sigma squared. You end up with a narrower distribution and one that's a little bit taller. And so you see here also the concentric ellipses have shrunk a little bit. Whereas in contrast, if you were to increase sigma to 2 on the diagonal, so this is now 2 times the identity, then you end up with a much wider, a much flatter Gaussian, and so the width of this is much wider. This is hard to see, but this is still a bell-shaped bump that's just flattened out a lot and it's become much wider. And so the variance here, the variability of x1 and x2, just becomes wider. Here are a few more examples. Now let's try varying one of the elements of sigma at a time. Let's say I set sigma to 0.6 there and 1 over there. What this does is this reduces the variance of the first feature x1 while keeping the variance of the second feature x2 the same. And so with this setting of parameters, you can model things like that. x1 has smaller variance and x2 has larger variance. Whereas if I do this, if I set this matrix to 2, 1, then you can also model examples where, here looks like x1 can take on a large range of values, whereas x2 takes on a relatively narrow range of values, and that's reflected in this figure as well, where the distribution falls off more slowly as x1 moves away from 0, but it falls off very rapidly as x2 moves away from 0. And similarly, if we were to modify this element of the matrix instead, then similar to the previous slide, except that here we're playing around. Here we're saying that x2 can take on a very small range of values, and so here this is 0.6, where notice now x2 tends to take on a much smaller range of values than the original example. Whereas if we were to set sigma to equal to 2, then that's like saying that x2 has a much larger range of values. Now, one of the cool things about the multivariate Gaussian distribution is that you can also use it to model correlations between the data. That is, you can use it to model the fact that x1 and x2 tend to be highly correlated with each other, for example. So specifically, if you start to change the off-diagonal entries of this covariance matrix, you can get a different type of Gaussian distribution. And so as I increase the off-diagonal entries from 0.5 to 0.8, what I get is a distribution that's more and more thinly peaked along this sort of x equals y line. Right? And so here the contour says that x and y tend to grow together, and the things with large probability are if either x1 is large and y2 is large, or x1 is small and y2 is small, or somewhere in between. And as this entry 0.8 gets large, you get a Gaussian distribution that's where all the probability lies on this sort of narrow region where x is approximately equal to y. There's a very tall, thin distribution, lying mostly along this central region where x is close to y. So this is if we set these entries to be positive entries. In contrast, if we set these to negative values, as I decrease this to -0.5 down to -0.8, then what we get is a model where we put most of the probability in this sort of negative x1 and x2 correlation region. And so most of the probability now lies in this region where x1 is about equal to -x2 rather than x1 equals x2. And so this captures a sort of negative correlation between x1 and x2. And so this is hopefully this gives you a sense of the different distributions that a multivariate Gaussian distribution can capture. So far we've been varying the covariance matrix sigma. The other thing you can do is also vary the mean parameter mu, and so originally we had mu equals 0, 0, and so the distribution was centered around x1 equals 0, x2 equals 0, so the peak of the distribution is here. Right? Whereas if we vary the values of mu, then that varies the peak of the distribution. So if mu equals 0, 0.5, the peak is at x1 equals 0 and x2 equals 0.5, and so the peak or the center of this distribution has shifted. And if mu was 1.5 minus 0.5, then again similarly the peak of the distribution has now shifted to a different location corresponding to where x1 is 1.5 and x2 is minus 0.5, and so varying the mu parameter just shifts around the center of this whole distribution. So hopefully looking at all these different pictures gives you a sense of the sort of probability distributions that the multivariate Gaussian distribution allows you to capture. And the key advantage of it is it allows you to capture when you'd expect two different features to be positively correlated or maybe negatively correlated. In the next video, we'll take this multivariate Gaussian distribution and apply it to anomaly detection. In the last video, we talked about the multivariate Gaussian distribution and saw some examples of the sorts of distributions you can model as you vary the parameters mu and sigma. In this video, let's take those ideas and apply them to develop a different anomaly detection algorithm. To recap, the multivariate Gaussian distribution or the multivariate normal distribution has two parameters mu and sigma, where mu is an n-dimensional vector and sigma, the covariance matrix, is an n by n matrix. And here's the formula for the probability of x as parameterized by mu and sigma. And as you vary mu and sigma, you can get a range of different distributions. Like these are three examples of the ones that we saw in the previous video. So let's talk about the parameter fitting or the parameter estimation problem. The question, as usual, is if I have a set of examples x1 through xm, and here each of these examples is an n-dimensional vector, and I think my examples come from a multivariate Gaussian distribution. How do I try to estimate my parameters mu and sigma? Well, the standard formulas for estimating them is you set mu to be just the average of your training examples, and you set sigma to be equal to this. And this is actually just like the sigma that we had written out when we were using the PCA, or the principal components analysis algorithm. So you just plug in these two formulas, and this would give you your estimated parameter mu and your estimated parameter sigma. So given the data set, here's how you estimate mu and sigma. Let's take this method and just plug it into an anomaly detection algorithm. So how do we put all this together to develop an anomaly detection algorithm? Here's what we do. First, we take our training set and we fit the model, we fit P of x by setting mu and sigma as described on the previous slide. Next, when you're given a new example x, so if you're given a test example, let's take an earlier example. Let's say I have a new example out here, and that's my test example. Given the new example x, what we're going to do is compute P of x using this formula for the multivariate Gaussian distribution. And then if P of x is very small, then we flag it as an anomaly, whereas if P of x is greater than that parameter epsilon, then we don't flag it as an anomaly. So it turns out if we were to fit a multivariate Gaussian distribution to this data set, to just the red crosses, right, not the green example, you end up with a Gaussian distribution that places loss of probability in the central region, slightly less probability here, slightly less probability here, slightly less probability here, and very low probability at the point that's way out here. And so if you apply the multivariate Gaussian distribution to this example, it will actually correctly flag that example as an anomaly. Finally, it's worth saying a few words about what is the relationship between the multivariate Gaussian distribution model and the original model, where we were modeling P of x as a product of this P of x1, P of x2, up to P of xn. It turns out that you can prove mathematically, I'm not going to do the proof here, but you can prove mathematically that there's a relationship between the multivariate Gaussian model and this original one. And in particular, it turns out that the original model corresponds to multivariate Gaussians where the contours of the Gaussian are always axis aligned. Right? So all three of these are examples of Gaussian distributions that you can fit using the original model. It turns out that that corresponds to multivariate Gaussian where the ellipses here, the contours of this distribution. It turns out that this model actually corresponds to a special case of a multivariate Gaussian distribution. And in particular, the special case is defined by constraining the distribution of P of x, the multivariate Gaussian distribution of P of x, so that the contours of the probability density function, of the probability distribution function, are axis aligned. And so you can get a P of x with a multivariate Gaussian that looks like this, or like this, or like this. And you notice that in all three of these examples, these ellipses, or these ovals that I'm drawing, have their axes aligned with the x1, x2 axes. And what we do not have is a set of contours that are at an angle, right? And this corresponded to examples where sigma is equal to 1, 1, 0.8, 0.8, let's say, with non-zero elements on the off diagonals. So it turns out that it's possible to show mathematically that this model actually is the same as a multivariate Gaussian distribution, but with a constraint. And the constraint is that the covariance matrix sigma must have zeros on the off-diagonal elements. In particular, the covariance matrix sigma, this thing here, it would be sigma squared 1, sigma squared 2, down to sigma squared n. And then everything on the off-diagonal entries, all of these elements above and below the diagonal of that matrix, all of those are going to be 0. And in fact, if you take these values of sigma, sigma squared 1, sigma squared 2, down to sigma squared n, and plug them into here, and plug them into this covariance matrix, then the two models are actually identical. That is, this new model using the multivariate Gaussian distribution corresponds exactly to the old model if the covariance matrix sigma has only 0 elements off the diagonals. And in pictures, that corresponds to having Gaussian distributions where the contours of this distribution function are axis aligned, so you aren't allowed to model the correlations between the different features. So in that sense, the original model is actually a special case of this multivariate Gaussian model. So when would you use each of these two models? So when would you use the original model, and when would you use the multivariate Gaussian model? The original model is probably used somewhat more often, and whereas the multivariate Gaussian distribution is used somewhat less, but it has the advantage of being able to capture correlations between features. So suppose you want to capture anomalies where you have different features, say where features x1, x2 take on unusual combinations of values. So in the earlier example, we had that example where the anomaly was with the CPU load and the memory use taking on unusual combinations of values. If you want to use the original model to capture that, then what you need to do is create an extra feature, such as x3 equals x1 over x2, equals maybe the CPU load divided by the memory use or something. And you need to create extra features if there's unusual combinations of values, where x1 and x2 take on an unusual combination of values, even though x1 by itself and x2 by itself looks like it's taking a perfectly normal value. But if you're willing to spend the time to manually create an extra feature like this, then the original model will work fine. Whereas in contrast, the multivariate Gaussian model can automatically capture correlations between different features. But the original model has some other, maybe more significant advantages too. And one huge advantage of the original model is that it is computationally cheaper. And another view on this is that it scales better to very large values of n, to very large numbers of features. And so even if n were, say, 10,000, or even if n were equal to 100,000, the original model will usually work just fine. Whereas in contrast, for the multivariate Gaussian model, notice here, for example, that we need to compute the inverse of the matrix sigma, where sigma is an n by n matrix. And so computing sigma, if sigma is a 100,000 by 100,000 matrix, that's going to be very computationally expensive. And so the multivariate Gaussian model scales less well to large values of n. And finally, for the original model, it turns out to work okay even if you have a relatively small training set. This is a small unlabeled examples that we use to model P of x, of course. This just works fine even if m is maybe 50, 100, it works fine. Whereas for the multivariate Gaussian, it is sort of a mathematical property of the algorithm that you must have m greater than n, so that the number of examples is greater than the number of features you have. And there's a mathematical property of the way we estimate the parameters that if this is not true, so if m is less than or equal to n, then this matrix isn't even invertible. That is, this matrix is singular, and so you can't even use the multivariate Gaussian model unless you make some changes to it. But typical rule of thumb that I use is, I would use the multivariate Gaussian model only if m is much greater than n. So this is sort of the narrow mathematical requirement, but in practice I would use the multivariate Gaussian model only if m were quite a bit bigger than n. So if m were greater than or equal to 10 times n, let's say, might be a reasonable rule of thumb. And if it doesn't satisfy this, then the multivariate Gaussian model has a lot of parameters, right? So this covariance matrix sigma is an n by n matrix, so it has roughly n squared parameters. Because it's a symmetric matrix, it's actually closer to n squared over 2 parameters, but this is a lot of parameters, and so you need to make sure that you have a fairly large value for m. Make sure you have enough data to fit all these parameters. And m greater than or equal to 10n would be a reasonable rule of thumb to make sure that you can estimate this covariance matrix sigma reasonably well. So in practice, the original model shown on the left that is used more often, and if you suspect that you need to capture correlations between features, what people will often do is just manually design extra features like these to capture specific unusual combinations of values. But in problems where you have a very large training set where m is very large and n is not too large, then the multivariate Gaussian model is well worth considering and may work better as well, and can save you from having to spend the time to manually create extra features in case the anomalies turn out to be captured by unusual combinations of values of the features. Finally, I just want to briefly mention one somewhat technical property, but if you fit a multivariate Gaussian model and if you find that the covariance matrix sigma is singular or you find it is non-invertible, there are usually two cases for this. One is if it's failing to satisfy this m greater than n condition, and the second case is if you have redundant features. So by redundant features, I mean if you have two features that are same, somehow you accidentally made two copies of the feature, so maybe x1 is just equal to x2. Or if you have redundant features, and maybe maybe feature x3 is equal to feature x4 plus feature x5. Okay, so if you have highly redundant features like these, where if I x3 is equal to x4 plus x5, well, x3 doesn't contain any extra information, right? You take these two other features and you add them together. And if you have this sort of redundant features, duplicated features, or this sort of features, then sigma may be non-invertible. And so there's a debugging step. This should very rarely happen, so you probably won't run into this. It's very unlikely you have to worry about this. But in case you implement a multivariate Gaussian model and you find that sigma is non-invertible, what I would do is first make sure that m is quite a bit bigger than n. And if it is, then the second thing I do is just check for redundant features. And so if I have two features that are equal, just get rid of one of them. Or if you have redundant features like these, x3 equals x plus x5, just get rid of the redundant feature, and then it should work fine again. As an aside, for those of you that are experts in linear algebra, by redundant features, what I mean is the formal term is features that are linearly dependent. But in practice, what that really means is one of these problems tripping up the algorithm, and if you just make your features non-redundant, that should solve the problem of sigma being non-invertible. But once again, the odds of you running into this at all are pretty low, so chances are you can just apply the multivariate Gaussian model without having to worry about sigma being non-invertible, so long as m is greater than or equal to n. So that's it for anomaly detection with the multivariate Gaussian distribution. And if you apply this method, you'll be able to have an anomaly detection algorithm that automatically captures positive and negative correlations between your different features and flags an anomaly if it sees an unusual combination of the values of your features.